Hi guys, this is the first video for the Mod 7 review. So this entire review for day one is no calculator. So for Mod 7, you guys will have a calculator portion of your test and a no calculator portion of your test. All these problems are fair game on the no calculator portion. Okay, so one thing we got to be able to do is take a exponential and rewrite it in log form and vice versa. So remember, the base is going to stay the same. So this is an exponential base 2, so it's also going to be log base 2. And then the input and output switch. Okay, so that would be log form. So this is the same thing, just going the other direction. So this is log base 2, so this one's going to be an exponential of base 2. And then the input and output switch. Okay, so that would be exponential form. This is log form. Okay. Now, being able to evaluate logs without the use of a calculator is also important. So I'm asking, remember, 2 to what power is 8? 2 to the third is 8. 2 to what power is 1/16? So 2 to the fourth is 16. Making it negative is what brings that to the denominator. Log of negative 10,000, don't let this trick you. Yes, 1,010 does go into, but remember, we cannot take the log of a negative. You can put DNE, does not exist. Or you can just say, actually, let's just stick with that. DNE does not exist. Okay. Natural log of 1. So remember, this is e to what power equals 1. Log of any base of 1 is always 0 also. Okay, here are two different ones. They're not the same base, so I can't combine these, but we already said, hey, log base 2 of 8 is 3, so we know that's 3. And then here, log base 5 of 25, 5 to the second power is 25. So if we evaluate each of those, 3 plus 2 is 5. Okay, here, 36 to the 8th is going to be a huge number. I don't have a calculator, so I'm going to apply that log rule of bringing that 8 down. So we have 8 times log base 6 of 36. So 6 to what power is 36? The second power, so this just becomes 8 times 2, which is 16. Okay. Graph. So for this test as well, you guys, we want to know what the parent functions of an exponential and a log function look like, and then we're just going to use transformations to graph those. So I'm going to graph the parent function really quick, okay, we'll do 2 to the x, okay, so that means my next point is at 1, 2, 2, 4, okay. Okay, so this is the parent function. This is y equals 2 to the x, okay? So remember, what this does is the thing in the exponent is moving left or right, always opposite of what we think. So this one's going to move left 1. This one is going to move down 3. So what we're going to do is we're going to take those points that I graphed and move them down 3. Also remember, the parent function has a horizontal asymptote at y equals 0. And I'm actually going to grab a pen really quick so you guys can see my graph. All right. Okay, so I'm going to move my intercept down 3. 1, 2, 3. And I'm going to move this nice point down 3. Okay. And then my asymptote of 0 also moves down 3. So I have a new horizontal asymptote at y equals negative 3. And then I'm just going to connect and get that same shape. Okay, so the red would be this graph. Okay, all right, let's do the same thing on this one. Okay, so I'm going to graph, this is log base 10, right, if there's no subscript. So my original log base 10 has an x-intercept of 1, and my next point's at 10, 1. And then it has a vertical asymptote at x equals 0. Okay, so it kind of looks like this, and then it gets really flat. Okay. Okay, so there's my parent function. So this is y equals log of x. Okay, so what this does, right, in with x, this is going to move it right, and this 1 is going to move it up. Okay, so we're going to take those 2 points and go right 2 and up 1. So right 2 and up 1, there's my x-intercept had moved to there. This one, right 2, up 1. Again, I'm kind of approximating with this one because it's off the graph. Since I moved right, any right or left is going to shift that vertical asymptote. So my new vertical asymptote is here. So vertical asymptote at x equals 2. And then get close, and this one's nice and flat. There we go. So the red is my new graph. Oh, and sorry, I forgot domain and range on these ones, you guys. Okay, so we're doing for the red. Domain of any exponential is all reals. The range depends on where our horizontal asymptote. So for this one, it goes from -3 to infinity. Remember, the asymptote we don't ever include because it never actually touches that value. For logs, our range is what's all reals, right? Inverse is the domain and range switch. Okay, now the domain is going to depend on the vertical asymptote. So for this one, it starts at +2 and goes forever to the right. And I don't include 2 for that same reason. The asymptote never actually gets touched. Okay, down here, this is just make sure you know the difference between log versus natural log. Log is base 10. Natural log is log base e. Okay? All right. Next thing is going to be using some of our log properties. So this is right as a single log base. Okay, so if we have addition and subtraction, we're just going to go left to right and do what we see first. So these have the same base and we're adding. Remember, we condense that as multiplication. So we've got log base 5 of 3 times 6, which is 18. Okay, now I can take care of the subtraction. Subtraction condenses to division. So we've got log base 5. The first term is my numerator. The second one is my denominator. We can go ahead and simplify that to log base 5 of 2. There's not a nice value that 5 raised to that power gives us 2, so I'm going to leave it just like that. If this was like log base 5 of 25, then I would want to go ahead and evaluate that further. Okay, this one says expand and simplify. So we're going the other direction here. Okay, so first, this exponent is applied to this whole thing. I'm going to pull that out front. So we have 2 times log base 6 of all this. So we've got 36 x to the 4th y. Okay, so these are all being multiplied, so we can split those apart through addition. Keep in mind, though, this 2 has to be in front of the whole thing. So I'm going to write it like this. Log base 6 of 36 plus log base 6 of x to the 4th plus log base 6 of y. Okay, so we've done almost everything we can. I do have another exponent. I can pull this down in front, and I can go ahead and evaluate log base 6 of 36. So we have 2. Log base 6 of 36 is 2. We can pull that 4 down in front. And we've got plus log base 6 of y. You can leave it like this, you guys, or you can distribute that 2 through. Either one would be acceptable here. Okay, and I'll show you the distributed one, I guess. If I distribute that 2 all the way through, here's what I got. So either answer there would be sufficient. Okay, we have the same directions here to expand. So I'm first going to split apart the fraction. So the fractions division, this separates into subtraction. So the numerator is the first one. So we've got x squared y minus log base 5 of 125. Okay, we again can split this into addition. So I've got log base 5 of x squared plus log base 5 of y minus, I can evaluate this. 5 to the 3rd power is 125, so I can simplify that. And then lastly, I can bring down that 2. So I have 2 log base 5 of x plus log base 5 of y minus 3 is as far as I can expand. Okay, next we have a solving example. Okay, so remember, if it's exponential, if I could write them using the same base, then I could set the exponents equal. So 27 is the same as 3 to the 3rd. So we're going to write 3 to the 3rd, and then that original exponent I'm going to multiply by 3. Okay, once these are equal, I'm setting the exponents equal. So we got 4x minus 1. Distribute that 3, we get 9 minus 3x. Okay, so I'm going to add 3x and add 1. So we have 7x equals 10. Divide by 7. We get x equals 10/7. And again, I'm not using a calculator, so I would leave my answer as that fraction. Okay? All right, last one here. I think the last one. Let me make sure. Yep. Okay, so last example. Solving an equation. Remember, I want to get rid of the log base 9, but I have to condense it to a single logarithm first. So this becomes 1 log base 9. Addition condenses to multiplication, so 6 times x. And then once my bases match, I can set the arguments equal. Or you can think about now, if I raise both sides to 9, it's going to cancel both of the log base 9. So we're left with 6x equals 2x squared minus 8. I have a quadratic. I'm going to set it equal to 0. Okay, and I'm noticing I have a GCF of 2, so I'm going to go ahead and divide everything by 2. So we have 0 equals x squared minus 3x minus 4. So are there numbers that multiplied before that add be 3, 4, and 1? So we've got negative 4 and positive 1 to get the proper signs. Okay, and now I set each of those equal to 0. I would get x is 4 and x is negative 1. Remember to check for extraneous solutions. So if I plug in 4, that's positive there, we're good. If I plug in negative 1, I cannot take the log of a negative in that situation, so negative 1 is not a solution, it's extraneous, and x equals 4 is the only solution. Okay, that's it for review day 1.